Hey there, we're going to work this problem together. This is from your Statics 3 assignment. It says, as shown in the picture to the right, we have a block that's at rest, and we're going to underline that word, right? That's one of those important words, on a horizontal frictionless surface. Two identical springs with spring constant 40 newtons per meter are attached to the block. Spring A pulls to the left, spring B pulls to the right, and forms a 37-degree angle with the surface. As a result, spring B is stretched 0.2 meters from its unstretched length, and they're asking us to calculate the distance spring A will stretch, and then what is the minimum mass that the block for this scenario to be possible. So let's kind of take a look. Let's start out, let's make our free body diagram. So we have the weight that goes down, we have the spring A that's going to the left, force the spring, and we'll put a little comma A there. Now we have the spring that is to the right, but it goes at a 37-degree angle there, so force of spring B. And we also have a normal force because it is in contact with the surface. Now you got to remember that there's an x and y component of the force from the force of spring B. So the normal force will not be the same length as Fg here. It's going to be smaller because now, vertically speaking, we have a normal force and a y component from that spring B. So there's our free body diagram. Let's go ahead and make our net force equations. So in the x direction, we have the x component of that spring B. So force of spring B, and I'm going to put x minus force spring A. And then in the y direction, so net force in the y direction, we have the normal force plus the y component of spring B minus the weight. So there's our net force equations. Now we know since we underlined that word it's at rest, we can set that equal to 0. Okay, so what that means for in the x direction, if I kind of expand this a little bit, that means that the force of spring B, the x component, has to equal the force of spring A. So knowing that, we're going to be able to solve for the force of spring A. Because in this problem, they gave us the spring constant. Okay, so the spring constant K was equal to 40 newtons per meter. And that was for both springs. And then they also told us how far spring B stretched. Okay, so spring B, so we'll put spring B, right, was equal to 0.2 meters. So that's how far it stretched. And remember, in our Hooke's law equation, force of a spring is equal to spring constant times the stretch. So this right here is the stretch for spring B. So we can then calculate the force exerted by spring B. So the force of spring B is going to equal the spring constant of 40 newtons per meter times its stretch, which was 0.2 meters. Now my meters will cancel. So the force exerted by spring B is just going to equal 8 newtons. So there's the force of spring B. And now we can use this information to find the x and y components of spring B. So if I kind of drew out a triangle, and we can say that this is 8 newtons, and this right here is a 37-degree angle. We can then solve for the x and y components. Okay, and that tells us the x and y components of that spring B. So for let's start with the x component. The x component is the adjacent side, and then the 8 newtons is a hypotenuse, so we're going to use a cosine function. So cosine 37 degrees is going to equal that x component divided by 8 newtons. So our x component, will multiply both sides by 8 newtons to get rid of that. So the x component is just equal to 8 newtons times cosine 37. And so we can write that out. The force of spring B, the x part, is going to equal 6.4 newtons. And while we're solving this triangle, let's go ahead and solve for the y part. So the y part would be the opposite side and the hypotenuse. So we would use the sine function. So that would give me sine 37 is equal to the y component all over 8 newtons. We'll multiply both sides by 8 newtons to cancel that out. So the y component of that spring B is just going to equal 8 newtons times sine 37. And what you should get for the force of spring B, the y part, is going to equal 4.8 newtons. So now we know the x and y parts of spring B. We know what the force of spring B is equal to. Let's go back over there to our net force equations that we had made. In our net force equation for the x component, we said that our x component of the spring B is going to equal the force exerted by spring A. And we just solved for the force of spring B, the x part. It was 6.4 newtons. So that just means that the force exerted by spring A has to also equal 6.4 newtons, right? Because it's balanced. And part A is asking me to calculate the distance that spring A is stretched from its unstretched length. So Hooke's law, remember, force of spring is equal to kx. And for spring A, we now know the force. That's a check. The problem gave me the spring constant, so now we can solve for the stretch. So rearranging this equation, we'll divide both sides by that k. So the stretch is just going to equal the force exerted by spring A divided by the spring constant. So we can plug in our numbers, 6.4 newtons divided by 40 newtons per meter. And now my newtons will cancel. So the stretch of A is going to equal 0.16 meters. So there is part A, the stretch of spring A. And looking back at the problem, for part B, it's asking me what is a minimum mass of the block for this scenario to be possible. So let's look at our net force equation that's in the y direction that we had made. Okay, right back up here, we said that in the y direction it was a normal force plus the y component of spring B minus weight is equal to 0. So let's rewrite that right down here. So normal force plus the y component of spring B minus the weight is equal to 0. So there's an equation we're going to kind of work with. We know we're going to use the y component one, because we're trying to find that minimum mass. So that's why we're going to use the y component here, or net force equation for the y direction. And since it's asking me for the minimum mass in order for this situation to take place, what we can assume is that the normal force is so small that it's negligible. Okay, so what we can assume here is that the normal force is equal to 0. So we can cancel this out. Because again, we're trying to find that minimum mass. And we'll kind of talk about our answer once we solve for this. So if that's the case, if the normal force is so small that it's negligible, that we assume it's 0, then that tells me that the y component of spring B has to equal the weight of the box. And earlier we found the y component of spring B and it was equal to 4.8 newtons. So that means weight is equal to 4.8 newtons. But be careful here because they want us to find the mass, right, not the weight. And we know that our Fg is just equal to mg, and we're going to rearrange that for mass. We'll divide both sides by g. That cancels. So our mass is going to equal the weight divided by g. The weight is 4.8 newtons divided by 10 newtons per kilogram. So the mass is going to be 0.48 kilograms. Now back to this assumption that we made. So if the mass is any smaller than 0.48 kilograms, then what would happen is that our spring would then begin to cause the box to move upward. Okay, if it's any smaller than that. If the mass is larger, then that just means we'll start having a greater normal force. Okay, and it's not going to lift up. But if we go smaller than this 0.48, then the block will start to rise off of the table.